Welcome to 50 Shades of Caching and how LLMs painted black. So my name is Effie. I studied physics. I'm an SRE at the Wikimedia Foundation. I have chaired SREcon a couple of times, and I will be your host for this session. Before we start, I have a couple of disclaimers. No LLMs were harmed during the making of this talk, and views here are my own and not my employers, unless you're Wikimedia donors, so you are my employers in a way. As I said, I work for the Wikimedia Foundation, the American non-profit organization running Wikipedia and its sister projects. And did you know that all Wikipedia content is managed by volunteers? We support over 300 languages. The project turned 25 today, this year. We have been training LLMs since they were called statistics, and we host some really extraordinary content, like the one about Lord Vader repeatedly running for office in the Ukraine. And please mind the gap between Lord Vader and Lord Buckethead, or Count Beanface these days. We also host quite a lot of scientific articles, as well as interesting essays like if you need to cite that the sky is blue, or maybe not. But if none of those things pique your interest, you can always check on the personal life section of your favorite supervillain. So let's start talking about caching. We'll try to sell you some encyclopedias along the way. According to Wikipedia, caching is a hardware or software component that stores data so that the future requests for that data can be served faster. And of course, it's everywhere. Your CPU, page caches to reduce disk access, databases, caching queries, CDNs caching and delivering web content closer to users, and your old browser is obviously caching. Why it's so important? It's important because it's crucial for my boyfriend to leave the milk on the counter since he knows I will be using it. It's important to keep your Wi-Fi password on a post-it on your fridge for your guests, or your Netflix password on your mum's fridge, as a matter of fact. This didn't age very well. Also, because caching security bugs are nasty and they have slowed down our processes, but you can't argue that the branding is amazing. Meltdown affected Intel CPUs that allowed attackers to read arbitrary memory. Spectre, tricking the CPU into fetching data it's not supposed to. Foreshadow, leaked data from L1 cache, even across virtual machines. Zombie load, spilling tiny pieces of dead data that wasn't supposed to be there. Cache out, letting attackers read data evicted from the L1 cache. And not picture, due to bad marketing probably, the cloud bleed, leaking chunks of memory into responses served to random users. Heartbleed is not a cache bug per se, but cache secrets will be stolen. So, just like we know our behavior and we decide what to cache and where, many caching systems do the same. So, caching systems are optimized to improve performance by analyzing human behavior. About this talk, I will be simplifying a few things here and there, meaning that I'm trading accuracy for clarity. It's a bit like the uncertainty principle, right, in physics. A talk can be both precise and comprehensible at the same time. What we have for today. So we're going to go through some caching basics, caching headers, browser cache, CDNs. Then we're going to go a bit deeper to the application layer. We're going to discuss cache invalidation, and of course, how everything goes to the bin due to LLM and AI agents. I promised that I will be simplifying a few things, and I meant it. So here is some really boring technology for you. We have your run-of-the-mill Apache PHP MySQL wiki about ducks. And according to Reddit, this is an exact depiction of the Wikimedia infrastructure. Which brings us to the CDN chapter. We can loosely say that we have two kinds of caches. I don't know if that is an official, two kinds of web caches. I don't know if that is an official term, but let's go with it. The private caches, which is your browser usually, and the public caches, which could be some proxy of yours, could be the big brother of your organization, could be a CDN. And the public caches basically sit between you and the backends. Now, usually caches are usually like a key value storage thing, right? They use a URL and various parameters as a key. So two identical URLs with different parameters are treated as separate items. Now, these parameters can come from the URL itself or from HTTP headers like accepted coding, user agent. So, for example, varying by user agent, you can get the cache will be different if this is a mobile site we're caching or if it is the desktop site. Moving forward, cache control headers define how long a response is good for and should be cached and by whom, private or public caches. And finally, cache invalidation headers are used to verify whether a cache response is fresh or needs to be revalidated. Let's get a bit more practical. This is a sample key entry of such. It's a sort of how the browser caches things. We have the key, the parameters, like the ones we just mentioned, and then beyond that we have the response headers, the actual body, and metadata, such as when this URL was cached, when it expires, determined by max age, and e-tag to use later if we want to check its freshness. So in a way, a web cache is just a pile of URL responses with metadata pretended it's organized. Now, a couple more practical examples. This is a request for the MediaWiki logo, which we don't change very often. And the date says that this response was generated. When it was generated, when it expires, and max age tells us this is good for another year. Which means that next time I request this, the browser, because of those caching headers, the browser will serve it directly from its cache, without even asking the server. The e-tag and last modified are backup validators. So after a year, the browser is going to use those that information to check if the cached content is still valid. And this is another example of a JavaScript. Notice that the server, again, serving that is ATS. We'll get to that later. Reading the cache control headers, we have max age, again, instructing all caches to cache for 10 minutes. Max age, instructing the public caches to cache for 10 minutes as well. But what does its stale revalidate 60 do? So public and private caches will cache for 10 minutes. At minute 9, the cache is good, and it's still fresh and served normally. And at minute 11, 1 minute past expiry, the cache will serve this stale content. So it will serve fast, but in parallel, it contacts the origin and refreshes the cached object. So by minute 12, we have either a new version of the object, or we know it's good for another 10 minutes. Last example here, this is a request for a wiki article, where we again have a date, when this was cached on the Edge server. Last modified, when the resource was changed, and this time cache control says private, max age 0, must revalidate. This means that browsers, and browsers only, that's why it says private, could potentially cache that, but do not serve it without revalidating that this is still good. On the server name here, you get the name of the pod that rendered that content. And that leaves us with the CDNs. So, as we said, they sit between the duck and the backend server. Why do we need them so desperately? CDNs work hard for speedy delivery. Pages loads fast with caching, static content, scripts, images, HTML, all that jazz. CDNs sometimes predict what the user is going to ask next, like the next video. They do some sort of routing because you're gonna get the content from the nearest server. So it's not routing, but anyway. Via Anycast, they offer reliability. You can imagine that a CDN is not just one server, right? the more cached content we have, the less load we put on the origin. They also add security. Usually TLS terminates on the CDN level. They offer DDoS protection. They absorb the bad traffic, and they can even, different kind of CDNs, they can also protect your entire IP space from DDoS attacks at layers 3 and 4. And lastly, during high demands, they can protect your origin server with various load shedding methods. This is our CDN. We have 2 main data centers in Virginia and Texas in the US, and which are also part of the CDN. And beyond those, we have 2 more in the United States, in the Americas, sorry, 2 in Europe and 1 in Singapore. Now, let's zoom in a bit to what is in a caching server, at least ours. I don't know what the others do. You can think of it, what's in the server, as an onion with different layers. So we have the HA proxy, which is an HTTP proxy with TLS support. In our case, it's doing the TLS termination. Varnish stores objects in memory. So this is where the hotter objects can be found. The ATS layer, the ATS layer, which is the Apache traffic server, also a caching proxy, storing objects on disks. Now, all these 3 services coexist in a single cache host. And I would like to also add that our load balancers support consistent IP hashing, which means that the same IP address probably will be routed to the same cache server. And they're also divided into upload and text. Upload is the cluster that for the media stuff, JPEG, images, videos, whatever, and text is for text. Last but not least, it's important to say that there's also a lot of application routing logic there, but it's beyond the scope. Before we conclude the chapter, there are some fun facts. So Zipf's law is an empirical law saying that your most popular item may be twice as popular as your second most popular item. And the outcome of Zipf's law is a Pareto distribution. 80% of your traffic comes from 20% of your content. In other words, if we're hosting 100 pictures of animals, most of the traffic will come from 20 of those. And the most popular animal, the dog, of course, has 20 hits per second, while the second most popular, the cat, has 10. But CDN caches are also regional. They have regional characteristics. There are areas in the world where the dog might not be the most popular type of dog, but it could be dingoes. So caches from region to region are different. Last but not least, they could help you with privacy law compliance, like maybe users have to accept the superiority of dogs before are able to view a picture of a dog, or maybe the picture of the dog is not even available in your region because, I don't know, someone bought it. And of course, sadly, censorship. Now that I've refreshed my memory with all the caches, I can re-interview for my position. Moving forward to application caching. Let's go back again to our basic rubber duck wiki, which is a basic LAMP site. We put the CDN and we reduce the work that our backend servers have to do. And we put in some, we're caching something on the browser as well. However, we can't cache everything. And our duck wiki is quite popular. It's vibrant. Articles being added, they be removed, edited. So we have to improve how the backend operates as well. So we're adding another layer of caching. So in the term application caching is also a loose term. We could probably divide application caches into 2 main categories, in-memory caching and external caching. In-memory caching stores things directly into the application's memory. So it's RAM. It's very fast, but it's also limited to the amount of memory we have. Sorry. Data is obviously lost if the application restarts, and typical examples include dictionaries in Python. And then we have the external caches, where data is stored outside of the app. They can be distributed, multiple nodes, they're scalable, fault-tolerant, resilient, such as memcached and Redis. So a little bit of warning, I'm going to use PHP, which I know is not very sexy, but it puts food on the table. So yes, you're going to learn more things for PHP than you ever wanted. So we're going to discuss PHP in-memory caches and one external one, memcached. So here's a crash course. PHP FPM is a process manager for PHP, and it runs multiple worker processes, each one handling one request. We can loosely say that PHP has two kinds of in-memory caches: opcache, which stores bytecode, and compiled PHP bytecode, and it can't be directly accessed, and the APCU, which is a user data cache, key value in-memory cache, where can be accessed by developers. And something you're really excited about, the life of a PHP request. When a user initiates a request, the web server picks up the request, which is then forwarded to the FPM process manager. This is delegated to the Zend engine. The Zend engine analyzes and compiles the PHP code into opcodes, blah, blah, blah. So those opcodes are temporarily cached and then executed. During the execution, if the script requires data, this is where we're going to contact the database. And then we get results, and the HTML is being sent back to the user. Now, if developers have specifically requested to fetch something from the APCU, the data will be fetched from there. What we can put to, what do we store in the APCU? Or language dictionaries, language lookup arrays, list of countries, configuration settings, environmental variables, whatever works. Of course, similar caches as such, like the APCU and the opcache, exist in other languages. Last time you see that, I promise. So we either want something from the database or the APCU, or we might need to fetch data from memcached, which is a distributed cache. So zooming out, we do not have like one memcached server, right? We have pools of memcached servers, and each cluster having multiple nodes. I do not really need to sell memcached here. It's selling itself. But I will mention some of the high-level stuff. Lead developer is Dormando. It's an amazing piece of software, and when it breaks, it's not it, it's you. It's key value memory, entirely on RAM. It supports disk storage as well, reduces memory waste fragmentation by using slabs. So it divides the memory in slabs, and each slab class has objects of similar size. And it uses an LRU-based caching system that treats data as hot, warm, cold before it gets evicted. At Wikimedia, we are using memcache to store various ephemera data, as well as fully rendered pages. By default, memcached is not distributed. However, the recent versions do have a built-in proxy, configurable via Lua, which we haven't tried yet. For the time being, we are, at Wikimedia, we're using Facebook's Mac router, which is a proxy router for memcached. It's transparent, so you can just use it. And its main feature is the advanced routing. It's advanced routing, like it supports sharding, replication, consistent caching, so each key ends in the same server every time. Supports failover. In case of dead nodes, there's always you can have a spare pool of servers to take over. And prefix routing means that developers can send specific keys to specific nodes or ensure that specific keys will be all grouped together in the same server. But it's also useful if you want to use like the same Mac router to route requests to different memcached clusters. So Mac router sits between our PHP processes and our memcached clusters, and the reason it looks like a leech here is because it exists as a daemon set in our Kubernetes cluster, so it's literally everywhere. Most of all, it has been battle tested and it scales easily and has been serving us quite well for years. I think we are hitting about 1.4 million requests per second. What's my crowd? I'm not sure. So yes, we briefly discussed the application caches, the in-memory ones, and one distributed memcached. Now, just like many good things in life, caches go from fresh to stale before you say, where's the Netflix password? And just like cache freshness, this will be a short chapter. So once upon a time, our cache was fresh. And via lazy loading on a cache miss, we fetch the data from the origin, and be that a backend server, be that our wiki, be that a database. Or we warmed our cache by a write-through. After an update, our application updated the cache synchronously. Or simply by pre-warming, like items can be proactively refreshed before they expire or upon changes based on whatever the developer decides. So, and there are many ways to invalidate the caches based on your layers and your general optimism. As a rule of thumb, it's usually cheaper to just let caches expire than to invalidate or delete them. Of course, we have time to live, expire the cache after a specific fixed time, write around, we update only the backend, and cache them on the next read. Write back, first cache first, tell the backend later, or explicitly clear caches through API calls. Versioning is quite interesting. It's like where we keep versions of keys and bump it in case there's a change. And the next time, on the next cache miss, this will be cached. And they're very, very handy event-driven, where an app emits messages that this should be invalidated, and the various layers that we have been discussing the whole time start invalidating. So this is where stuff like Kafka come in, but I'm not going to get into that rabbit hole now. So the really short version is that browsers and CDNs cache responses for URLs. Application layer caches store data that we need to build those responses. Now, in this section, I'm not going to share anything super exhausted or super exotic or super deep. It is a topic of how LLM scrapers grow the internet, and if it's something that has never come up to your workplace, tell me where you work. And short disclaimer, this is not a project I'm actively working on. I have not been drafted in this battle against bots. So material here is work of my colleague Giuseppe and Chris. So what I've been discussing this whole time is a long version of saying that we have optimized our systems for human traffic. And as users, surfing the internet in a similar manner, they're scrolling down pages, they're clicking on posts, clicking down, yada, yada, yada. There's a pattern. So we all try to budget our capacity to handle traffic spikes. And the latest PayPal announcement is where we brought our all-time traffic, peaking at 800K requests per second, which is more 6 times than our usual traffic, and an ingress bandwidth of 134 gigabytes, which is twice. And in the past, when we had traffic anomalies that were not linked to any ongoing events, it was usually something funny, like a flower hitting 90 million views a day in India because some mobile operator pushed something, or a PhD student not understanding request concurrency. So in a way, we build our systems to bend when the circumstances demand, but not break. And this is where it all falls apart. LLM crawlers and AI agents are increasing the web traffic. And you can find articles by Cloudflare, Fastly, Akamai around this topic. It feels like every AI startup is hoovering the internet. And they don't just scrape HTML. They also like breach media with detailed metadata, like what we have in Wikimedia Commons. It's all training material. A few months back, we spotted a scraper in Singapore, hitting our point of presence in Singapore for media files. But because those were not cached, we saw our connectivity between our main data center and Singapore to be exhausted. So we see the link being saturated. And since January 2024, we saw a 50% increase in bandwidth usage, mostly used by, sadly, bots. And the thing is that, unlike older bots, they do not play nice. They ignore robots' text. They're usually distributed, coming up from small, big cloud providers. They're unpredictable. Today, they are scraping the letter A, Bollywood actors next. They will try to do reviews next time. And most of all, they are trying hard to pretend they are something else. They impersonate the Google bot. They impersonate other LLMs or other AI agents. And they are trying super hard to impersonate humans. So residential proxies are the new Blαck. And if you're not aware of what this is, they route traffic through ordinary residential internet connections, which is pretty shady, as it is often unclear whether the users truly gave their consent or they just installed a free VPN extension. So your mom's fridge could be training some startup's LLM. And while we may not have paid subscription to ChatGPT, Claude, and all that stuff, we're all paying for LLM training, one way or another. Traffic costs, computational costs, power consumption, monitoring fatigue from people playing whack-a-mole with the next robot that is scraping the website. And it's something that everyone is affected by, right? Articles, blogs, news, media, code review platforms, event systems, but mostly our users, because sometimes there's not enough resources for the users to actually read the page. So why don't we just cache everything, right? This is an actual place in Canada. They have good rates in SREs, I reckon. It's very naive to say that we can cache everything, but it's not how things work. Dynamic responses, URL parameters, different versions of page, gzipped, uncompressed, mobile, desktop, different languages, left and locals. And then if we will put media in the mix and cache invalidation and multiply those by every single point of presence we may have, it just doesn't scale. I mean, right now, I think we have about 1 petabyte of media stuff at Wikimedia. It feels sometimes like having shops in Italy making Hawaiian pizza, just in case some tourists will turn up and eat it. So the data is constantly changing. Articles are being edited hundreds of times. One change in one article can require changes anyway. In other places. And also cache is regional. There's no need to cache stuff in one region that's never going to be fetched. So, can we strike back? It's not an excessive list of what we can do or what everybody has been doing. And it's not a project I'm working on. So, one thing is definitely dealing with dump crawlers, banning ancient user agents, and operating systems. It's a good start. Like, it's unlikely that Internet Explorer 6 is doing any science. IP reputation services can help us categorize traffic and apply the relevant, and we can apply relevant limits. And also, same goes for cloud providers. And make use of some crawler databases that exist, and some of them are free to use, I reckon. Lastly, we can add some browser-level checks like cookies, JavaScript, headers, JA and JA3 and JA4 fingerprinting, which are super interesting. Because with JA fingerprinted is a method where we identify clients through their TLS and HTTPS handshakes, like cipher suits and extension. So it's easier to be able to find, regardless where the bot is coming from, it's easier for us to know it's the same bot. So what I'm describing here, it's basically web application firewalls, which started as pattern and rule matching stuff, but now vendors are layering machine learning. We discussed a lot of things today. Where does that leave us? The Terminator was wrong. Skynet is going to scrape all our websites till we run out of resources. And it's becoming a war with robots against robots. Robots deciding if a robot is a robot pretending to be a robot or a human. So if it is a fight of robots against robots, why am I still getting paged? That is all. Thank you.